This week we are doing digital electronics, an introduction. So the next 2 weeks we'll be doing digital logic and digital systems, and there will be some digital systems on the mid-semester test in week 7, just to let you know. Okay, so what do we want to learn today? So you may have heard the term digital thrown around and analog as its opposite. We want to be able to explain the difference between digital and an analog representation of signals and data. So I've got an analog signal, I've got a digital signal. What are the differences between the two, and why is the digital representation good or bad? Nothing is absolute in this life, so the digital representation does have many advantages, but it also has some disadvantages. And just to end today, we want to explain the concept of what we call noise margins in digital logic and digital circuits. Okay, so what is digital? If you take a dictionary definition, one definition is it relates to fingers, the digits on your hand or your fingers. That's not really what we're talking about, but it sort of is. For those who've watched Star Trek, have you heard the phrase "live long and prosper"? No, over your heads. Probably a generation before, but to make that sign, the person who played Spock in Star Trek had to glue his fingers together. I don't know if it's easy for you to do. I can do it, but apparently the actor who did it couldn't. That's a little bit of trivia. What else does digital mean? It means, another dictionary definition, involve or relating to the use of computer technology. We're getting closer to what we're talking about, but still not quite correct. Okay? So you hear, oh, it uses a computer, it must be digital. Sort of right, but sort of not. So here's our engineering definition. So when we're talking about signals or information, something digital is when that information is represented in discrete values. Okay, remember what discrete means? So the difference between discrete and continuous. So the value of the physical quantity can only be a certain number of values, not an infinite number of values. And this could be, say, the voltage that represents the sound coming out of a microphone, or the voltage that represents the quantity of temperature coming out from a temperature sensor, for instance. And this graph here might show a good a good way to distinguish between something digital or analog. So if you can see here, you've got this grey line, and that grey line on the vertical axis is continuous. The value of the grey line can be any value between these two in this range, right? There's an infinite number of values that grey line could be. However, for this red line on the vertical axis, the range of values for the red line, the range of values that this red line could be come in discrete steps. So it could be only, whatever this is, this could be 4, this could be 5, this could be 6, this could be 7, okay? So that's the primary difference. We represent a signal or some data in discrete numbers of steps when we're talking about a digital system. Okay, so what are the advantages of doing something like this? Why is it better to be able to say, categorize something into, say, four different steps as opposed to, say, an infinite number of steps between the range of those 4? Well, this allows us to use some different operations, some digital computation. So if we wanted to do this in analog, say we wanted to add 2 numbers in analog, you could use, say, an op-amp. And the op-amp could add 2 values of voltage together. But the problem is that when you add those 2 values of voltage together using an analog device, the result may not be very precise because those values tend to fluctuate and there's noise in the values of the voltages you're adding together. Some of the circuits that you construct to work with digital numbers or digital logic are very simple to use. And we'll come across that in the next lecture. We'll come across logic gates. We can contrast logic gates to operational amplifiers. Digital storage. So one of the major benefits of the digital approach is that we can store data, and the storage of the data is very robust. The data that's stored on, say, your hard drive. Sorry, has anyone heard of a floppy drive? Has anyone used a floppy drive? Wow, that's a much bigger response than I've ever had in the past. Okay, so you know on a floppy drive, a floppy drive is still digital storage of data, but the data on the floppy drive degrades very quickly because it's stored badly, right? On a hard drive, it's stored a little bit better, but back before that, we would store data as analog on, say, a tape. Has anyone used a tape to store anything before? Yeah, like an audio signal. You put it into your car stereo, if you had an old car stereo, and eventually you would find that the audio signal it would degrade over time. You play it 100,000 times, and your song that comes out of it is pretty mangled up by the end of it. Well, digital data storage allows us to make exact copies of data, and the data, as long as you're careful about it, the data lasts a very long time and is quite reliable. Also, now that we've developed a really big silicon computer industry, we can store more and more data in the same amount of space. So if you have a look at this diagram, I don't know if it's very clear, but in 1979, this giant contraption here, this was a man, this was a hard drive, stored 250 megabytes. Megabytes! Over here, you've got a man's hand and a flash card or micro SD card that stores 16 gigabytes. That was last year. You can't read it, but this hard drive back then costs tens of thousands of dollars. This SD card cost $11 and stores probably 4,000 times as much data on there. Well, that's just a number I plucked, but I didn't do the math. So because we've got a well-developed silicon industry, we can shrink a lot of electronics and increase our storage size because we're using digital storage. Here's an ancient flash drive. It's not really an ancient flash drive. It's just a piece of concrete with something sticking out of it. It looks like a flash drive. But even better, here's the world's largest USB flash drive. It's not really the world's largest. It's a building with something that looks like a thing sticking out the top and makes it look like a flash drive. Anyway, digital communications is the other major advantage of digital signals. Okay. Now, we said that we could use amplifiers, in particular, to amplify a signal to travel long distances. That's great, but when we're using amplifiers, amplifiers introduce noise, okay? And that noise, every time you amplify a signal, that noise grows and grows and grows. So if I amplify a signal 100 times, every step of that amplification gives more noise. That's with any amplifier. If I use analog signals, then I can't distinguish the noise. Well, it's very hard to distinguish the noise from the signal. If I use digital signals, we'll see that it's very easy to get rid of the noise from a digital signal. And finally, the other major advantage of the digital approach is digital circuits. So digital circuits are really easy to construct. They're very robust in terms of that they can tolerate a lot of error. And you can manufacture a lot of them onto a very small, let's say if I had a silicon wafer about this big, you could probably fit maybe 50 to 75 CPU, like computer CPUs on them, central processing units, on that one wafer. And they're very programmable because they're reasonably easy to understand. So here's an example of digital computation. So I said that digital computation is easier than analog computation. Here's one easy example to show why analog computation is sometimes not a good idea. So here's an op-amp. You know what it does. It sums two values together, all right? And it does this via the ratio of the resistors. you've done this for the last 2 weeks. And let's say you had voltages that represented an amount of money, and you want to add them together. So you've got $1,000 in your bank account, and you put another $1,000 in of your earnings for the week. Well, using this summing op-amp, I would add these together and come out with a number. But you know what? Real devices have tolerances, like resistors. So this resistor here would be 10K plus or minus, say, 0.5K. And if you do the calculations, depending on whether you get a plus or a minus for this particular exact resistor, you could get out a range of values for the amount of money that was put into your account, well, the total in your account. So if you're lucky, you get an extra $100. If you're unlucky, you lose $100 just because of the analog computation. Okay, so this is obviously not a good idea for our banking system. So this is where digital computation comes in. We can make nice, exact, well, close to exact calculations. Digital storage, so data used to be stored in computers on tapes, and these tapes would have, these stripes would have different values of magnetism on them, different strengths of magnetic field on them. Unfortunately, what happens is that magnetic field over time tends to decay with exposure to the environment. And so what used to be your favorite song turns out to be just a whole load of white noise over a long amount of time. Digital storage does not suffer from this problem because what happens is you don't look at the strength of this magnetic field, you just look at whether there's a magnetic field there or whether there is not a magnetic field there. So that's much easier to tell than if I'm trying to figure out the exact value of that magnetic field. So it's either there or it's not. And that's easier to figure out. Communications. So as I said, amplifiers introduce noise. So here's our initial signal. That signal has decayed to something really small over here. When I re-amplify this signal, this amplifier introduces noise. Okay, and if I've got this signal here and I introduce a little bit of noise to it, every time it gets amplified, I end up with a bit of noise at the end. And that's why over a long distance, it's better to use digital communications, because what happens, instead of amplifying this, if I have a digital signal here, right, and then this signal's small here, and I introduce noise to it, well, that's okay, because there might be a little bit of noise there, might be a bit of noise here, a bit of noise here, a bit of noise here. But every time I regenerate it, that noise has less significant effect on our signal, because all we care about is whether the signal is one of either a high value or a low value. We don't care about the exact value of our signal. So this is analog, and this is digital. Okay? So if we only transmit a high or a low signal, then the communication can be more resilient to noise. And that's exactly what we do. We transmit high and low signals as opposed to trying to transmit what's stored, well, trying to transmit an analog signal. So a key difference, you know your old FM radio? You're driving along and you hear static on it every now and then just because you get interference from different areas. So who's got a digital radio in their car? Anybody? Or digital radio in the home? You'll notice that you don't get that static interference effect anymore. Either the signal works properly or it doesn't. Or let's say, anyone had analog TV before it was switched off? Yeah, you get ghosting and you get interference. Well, with digital TV, you don't get that, right? You either get the full signal or you get nothing. You get a whole lot of garbage. But it's a lot more robust to noise in general. And digital circuits. Here, this is actually what an analog computer used to look like. If you go to the ECSE department on level 1 on building 72, down the end, there's a room, and in that room, there's a whole load of relics. And you'll see a number of analog computers. So what these were is these are all dials and potentiometers and op amps, and you connect things together depending on what kind of calculation you want. You slide to get values of resistance, and you put in an input signal and you get an output signal. Problem with this is that all of these, if you want this to be a good computer, all of these components must be really, really exact and within a tight tolerance range. We don't have this problem with digital computers. In fact, a lot of digital computers, often what they do is they'll make a whole load, they'll test all of them. The ones that don't work, they just chuck out, and then they send you, they ship out the ones that do work. So imperfect. So in the analog world, if you made an imperfect analog computer, then it's totally screwed. You can't use it. In the digital world, you make a bad one on silicon. Well, it just gets thrown out. You've made 50 others, so it's got a higher yield. And these things are harder to program too. Digital computers. Who's done any programming? Who's ever written a Hello World program? Pretty easy, right? You try doing that with an analog computer. I'll tell you, it's not easy. Okay, so much easier to program, which probably is one of the foundations of why they're so widespread. Okay, so hop on, Melt's question, just to see if you understand the difference between analog and digital from what I've been saying. It's pretty easy. Answer that. Saying that, I did ask my wife this question last night, and she couldn't get it, but probably because I didn't explain it well. All right, there we go. So which of the following is a digital quantity? So if you have to think about what the actual quantity is and what range of values can that quantity take. So if the range of values is continuous, then it's an analog quantity. If the range of values is discrete, then it's a digital quantity. So firstly, does everyone know what discrete means? Discrete means a integer number of values that it could be. Okay. So what range of values could temperature take in general? What range of values could a state of a light switch take? What range of values is the velocity of a horse? What range of values is the waiting time of the bus? If I asked you, is whether you are late or not late a digital quantity, what would you say? Is that digital or is that analog? Analog. So you could be sorta late, or is it just late or not late? So it can be only two states, right? You can either be late or not late. So that would be digital, an example. All right, so looks like most of you, well, pretty much everyone. Did I sway someone with the velocity, with the waiting time, late or not late? No, it's definitely, all right, there we go. It's definitely the state of a simple light switch, right? So I managed to switch off, okay. Yes, so there's a prime example of a digital device, is a simple light switch, right? So I said this to my wife, and she goes, "But what if there's a dimmer on it?" I'm like, "Oh, damn it!" So I made a simple light switch with no dimmer. Okay, so that's pretty much the principle behind how you would create a digital, well, distinguishing digital and continuous systems. Continuous being analog. Okay, so now with that definition out of the way, what's one of the first things that we need to, well, let's learn about some actual circuits and what happens when we try to introduce this digital type theory into electrical engineering. Okay, so what we do is, instead of representing data as continuous signals, modern computer systems now represent everything as sequences of ones and zeros. Okay? So any idea why you would do 1 and 0? Why wouldn't I do levels of 1 to 10, for instance? Yeah? Yep, so it's on or off. You could have a big difference between the ranges of on and off. So if I've got this much noise, and I've got this much difference between on and off, then it's quite likely that this noise is not going to affect my ability to distinguish whether someone told me something was on or something told me was off, right? Yeah, so having 2 levels is good. If I had 3 levels, so if I had 1 level here, 1 level here, 1 level here, and I had that amount of noise, well, then it starts getting a bit fuzzy. Like, how do I know that something here was actually the middle level or was it the bottom level? Okay, so the more levels you have, the more tricky it gets. So that's why 2 levels, or 1s and 0s, tends to be the best, gives you the best differentiation between 2 values. And also, this is not just that, but also these are very easy to represent and very natural to represent in electrical engineering. You just represent something as a high voltage or a low voltage, right? Easy. I can define high voltage as 5 volts. I can define low voltage as 0 volts. And if I send a high voltage, I think, oh, I got a 1. If I send a low voltage, I get a 0. Very, very simple. Okay, some definitions. You can work with, this is not an outlook to life, but you can work with what we call either positive logic, and in positive logic, anything which is high is always referred to as the 5 volts, say. So 5 volts we may call as logic 1, or high, or true, or on, or active. And the opposite of that is that logic zeros, or voltages close to 0, are called logic 0, low, false, off, or inactive. Okay, so that's in positive logic. There are schemes and systems where you can use negative logic, where this is reversed. So if I talk about a 1, I'm actually talking about a 0 volt, and everything is switched between positive and negative. Pretty obvious once you understand what positive logic is, but important to define because, of course, by Murphy's law, if someone had done something in positive logic and you didn't tell the other side, well, what are they going to do? Someone is going to interpret everything as negative logic because that's how they work, and then disaster. Okay, so now here we've said, okay, so we represent 2 values as voltages, as 5 volt or a 0 volt, but now you're telling me that there's this thing called noise, and noise gets into everything. So what we have to introduce is the concept of noise margins. Okay? So with that, there are actually many families of logic devices, okay? By a family of logic device, I mean there are many ways to create little types of circuits that can give you the same effect of creating a logic circuit. And each of those ways of creating the devices have their own specifications of what logic 1 and what logic 0 is in a particular voltage range. Some might be 0 volts and 5 volts, so that might be low and high. Some might be negative 5 volts and positive 5 volts. Some might be 0 volts and 3.3 volts. Okay, so should be pretty obvious that if I'm using devices from different families, you're going to probably get some errors in if you try to connect these devices together. But we'll go through that now. So these devices, if they're within the same family, they'll be designed to work reliably. So if I have one logic gate here, that talks to another logic gate here, right? And these two are of the same family. Let's say they're both TTL, transistor to transistor logic. Then if I put signals in here, then the signal I get out here should be correct. If I decide to use a different type of gate here, then where all bets are off, you may or may not get the correct computation. Okay? But even before you get to that point, within the same family, you need to ensure that everything is reliable. And to do that, you need to make sure that you've got some margin for error for the voltages that represent a 0 volt or a 5 volt. Oh, sorry, a low and a high voltage. Okay, so here's an example of how how errors occur. Even for a very simple case where on your computer you've got, say, the CPU, and that CPU is only located centimeters away from the RAM, or the memory, so the microprocessor CPU, the memory is your RAM. Even for that short distance, because of the speed that these technologies operate at and the electromagnetic environment around it, you can get interference coming even in that little short distance into the wires that connect those two computer chips. Okay, so we need to ensure, so it's no good if your microprocessor sends data and it doesn't get to your memory correctly. We need to ensure that that actually works and that a transmitted 1 is always received as a logic 1 and a transmitted 0 is received as a logic 0. So how do you do that? Well, what we have in these gates, before I introduce the word gates, in these logic devices is a margin for error. So let's say this is our sending device, this is our receiving device. Well, even when the sending device thinks it wants to send a high signal and requests that we send a high signal at, say, this voltage, well, when it sends a signal at this voltage, you've got noise, and noise can be quite big. Okay? So at the receiving end, we have to have a range of values which is considered to be a logic 1 in this case. And the difference between the range at which is a logic 1 is transmitted and the range at which a logic 1 is received is called the noise margin. Okay, so as the name suggests, it's a margin, which is a difference between two values here, for noise to affect our signal. Now, unfortunately, you can't catch everything because if you have really large spikes of noise, then that could change our signal so that it's outside of the range of this receiver. And this does occur, and when this occurs, this is called a bit error. Okay, and you can't do anything about that. There are random acts of nature that cause this, and there are also not so random acts of nature, such as somebody poking it with a stick or somebody electrocuting themselves. So you can't get around that, right? But there are ways that you can minimize that, and we won't go over those. That's for like second year type stuff. Okay, so similarly, if I send a low voltage value, you want to have some sort of margin for error which says that anything received up to this value we interpret as a logical 0. So on this side we say, oh, it's a 0. On this side we say, oh, okay, I did receive a 0. Oh, what's that? What did that say? Oh, 0, okay. So again, anything, if there's noise that brings this outside the range, well, we'd say this is error, right? And the worst kind of thing that could happen is if it goes into the range where it's received as a 1. So we transmitted a 0, but the other end inadvertently thinks it's a 1. And if your computer system's not designed correctly, this can crash your system because it'll make your computer do wrong things. And there are ways to counteract this as well, but not anything that we will cover. Okay, so you put everything together, and in the end, you should have a computer system that will send signals. So when I'm talking about a high signal, I'm actually talking about a range of voltages from this VOH minimum to whatever the maximum voltage is. Let's say that's 5 volts. And when I'm sending a logic 0 or low, I'm talking about a range of voltages down here from 0 to VOL max. Okay? So it makes it nice and easy for us to just think about high, low, instead of thinking about, oh, it has to be a range of values that represent a high or low. Now what happens, what happens when we start connecting different types of logic families together? Well, for example, here, this is one type of family. Who's heard of this term before? CMOS, CMOS. Okay, so that's one way in which we construct logic gates. One type of manufacturing technique that constructs logic gates. Okay, so this is an example of the CMOS type of profile for logic 1s and 0s. Okay, so when a CMOS gate or CMOS device sends a logic 1, it will send a value of voltage which is really, really tightly defined. It's like 90% of V supply, and let's say V supply is the maximum voltage. Could be 5 volts. Then V supply, if I send a logic 1, the manufacturing characteristics will make it so that this will always be between this range for logic 1. And down low for logic 0, it's a very tight range for a 0. Okay? And the receiving end has quite a large noise margin that is well defined, and it's like something like 30% or lower of the V supply will be received as a 0, 70% or higher will be received as logic 1. Anything in between is an error. Okay, so that's CMOS. That's one type of logic family. Here's another type of logic family. Oops. Okay, so TTL, transistor to transistor logic. So this is a different type of manufacturing process. They're different devices, but they can still be used for digital logic. Well, in this case, a logic 0 goes from 0 to 0.4 volts, and a logic 1 goes from 2.4 to 5 volts. It's really different, right? And over here, there's very small noise margins. So noise margin here is quite small, noise margin here is quite small. But anything from 2 volts upwards is considered a 1, and anything from 0.8 volts below is considered a 0. So you can guess what happens next. Well, let's say we connected a TTL sender. Over here, you've got a TTL transmitter to a CMOS receiver. Well, your TTL gate goes, oh, okay, I can send a 1, and the 1 is in any range here. Anything, because I know that when I'm talking to my mates, when I say a 1, that could be anything from 2.4 to 5 volts. Well, okay, just so happens that I sent a logic 1, which is at the minimum range of acceptable logic 1s, 2.4 volts. Well, my CMOS receiver says, whoa, hold on. I don't understand anything between anything that's less than 70% or greater than 30%, so this is going to give me an error. Okay, so this is key example of why you don't use different types of logic gates together, because inevitably you're going to run into issues where they don't match on their logic values. Okay. Okay, so that's all well and good. So you've got these logic gates. When you connect them together, with the rest of the time that we do digital logic, we're not going to talk anything more about the actual, nitty-gritty of the gates. So some practical considerations, which I'll talk about now, are that when you make logic circuits, and you'll be making logic circuits on paper and using the chips in your lab, they won't be very big, but you'll see that they become very big if you're going to do something really useful. Well, the thing is that these gates can only, just like op amps, they can only give out a certain amount of current. So you might be tempted to do something like this. Here's the output of gate 1. And you might be tempted to go, okay, let's take this output and put it into 50 other gates. Let's take this result from here and put it into 50 other gates. This is not a good idea because these logic circuits can only give a certain amount of current, let's say 100 milliamps. Okay? It's pretty logical, pardon the pun, but not something you may think of when you're designing these things. Similarly, these logic circuits will only sync or allow a number of logic zeros. 10% run. Okay. I'm nearly finished anyway. It's not going to affect us. Okay. Similarly, logic gates will only allow a number of logic zeros. You can't connect 50 gates and expect it all to work off one output. Most of these details will be on the data sheets. They'll tell you how much current you can provide and how much fan out or how many number of gates it will drive. And finally, as with analog circuits, okay, so we remember these things we talked about, supply bypass capacitors on op amps. So on the supplies, we put capacitors here. Oh, sorry, bad drawing. On our V supply, we had capacitors here. And the reason for that was to smooth out the supply voltage. Well, exactly the same thing you should do on digital gates. Okay. In fact, digital gates are worse than op amps. So if you don't do this with digital gates, you're going to get more errors than you would if you were using op amps. Okay, so always use supply bypass capacitors. Logic gates need really well-regulated power supplies, and that ties in with these supply bypass capacitors. This goes without saying because if I went back to this and I said, particularly with the CMOS example, right? CMOS will look at the voltage levels relative to the maximum voltage, and if that maximum voltage fluctuates up and down, then it goes without saying that these levels all will fluctuate up and down. Okay, so you need to make sure that this V supply level is really, really well defined. Okay, and that's what this is talking about. And finally, similar to having a well-regulated power supply, you should make sure that the logic zero levels are really, really stable as well. So usually, logic zero is 0 volts, and a 0 volt usually means you connect it to some sort of ground rail, right? So you would have 0 volts, and that's connected to ground. Well, the best way to do this is you have a ground sheet, just like we talked about with the op amps. Okay, so this is a 0 volt, it's a copper sheet, and you have all your logic gates, and you connect them to your copper sheets, a big sheet of copper. And because this big sheet of copper can dissipate a whole load of current really, really effectively, then the voltage level of this sheet remains really, really stable at 0 volts. Okay? Or whatever voltage you connect to, usually 0 volts. Okay, so that's it for the introduction to digital systems. On Wednesday, we're going to start doing a lot of little binary and digital calculation type stuff. So this was just a nice little intro.